So good afternoon, everyone. So recording is in progress, so whatever you say, it will be recorded, just remember. It is a great pleasure to welcome Matteo Guainazzi today as colloquium speaker. So we invited him today here to talk about Athena. And I tried to do my research in order to figure out who you were. And what I found was a newsletter from Athena from 2018, where you introduced yourself to the team. So this is the only thing I found. So from that, I reckon that you have been involved in ASCA, Beppo-Sachs, XMM Newton, and where I guess that's where you have been in contact with Manuel. You are interested in AGNs and high energy emission as in general, so therefore I find it in particular pleasant that you are here to talk to us about the new version of Athena, such that we can potentially figure out where science interests are crossing. And with that, I would like to invite you to give your talk.
Switch on, and I'm ready. Do you hear me? But above all, the people online, do they hear me? I hope so. So thank you for the invitation and the introduction. It's a pleasure for me to be here to talk to you about New Athena. New Athena is the new incarnation of an idea that has been going around for more than a decade now, for a large X-ray observatory led by the European Space Agency, for whom I work. Moment. I have to say that I got it. And then the other way. Okay, I'll do it in a different way. Oh, no, it's complete. Okay. Okay, sorry for the hiccup. So what I'm going to show you today is first providing you with a general introduction of what Athena used to be, because Athena as such, as a mission, does not exist any longer. So this will lead me to lead you through a short journey towards the main scientific themes of Athena that are related to galaxy cluster, large-scale structure, compact object, AGN, and other powerful events in our universe. After that, I will concentrate more on the specific contribution that we expect a mission like Athena and hopefully New Athena in the future will be able to deliver on stellar and exoplanet science. Now, as I was introduced, my scientific expertise has nothing to do with stars, has nothing to do with planets. I mainly deal with the high energy emission of active galactic nuclei. So what I did, what I'm doing in this presentation is to present the collective wisdom of a large community of scientists who have developed the science case for the mission on stars and exoplanets. And in particular, I have to thank the few colleagues, Marco Dard from the University of Geneva, Fabio Favata from ESA, Rachel Osten from the Space Telescope Institute in the US, Jorge Sanz Forcada working in Spain at the CAB, who have allowed me to find my way through the recent literature, provided material, and they are the main intelligence on this specific topic in this presentation. But of course, any inaccuracy or mistake is solely my responsibility. And last but not least, I will briefly explain you what is the transition between the Athena concept, on which most of the science simulation that I'm going to show in my presentation were based, and a new mission concept, which is New Athena, that ESA is considering in this moment. Now, so what was Athena? Athena, first and foremost, was a large-scale X-ray observatory. And my stress here is on the word observatory. Now, Athena was designed to address a few specific questions in modern astrophysics that are embedded in the, let's say, themes of the hot universe and the energetic universe. The hot universe means we want to study how the large scales, the baryons locked in the large scale structure of the universe, formed and evolved. And we use, in order to do this study, primarily galaxy clustering groups, so areas of the universe where you have the density of galaxies billions of times larger than the density of galaxy in the local universe. You can have hundreds and thousands of galaxies in the same volume encompassed between the space between the Milky Way and the nearby galaxy Andromeda. And the second important theme is the energetic universe. We want to know how accreting supermassive black holes shape and affect the cosmological evolution of galaxies. And we know nowadays that most massive galaxies, probably all massive galaxies, host massive black holes at the center with a mass between million and billion times the mass of the sun. But I would like to stress once again the fact that Athena is an observatory, so it was designed also to be able to perform measurements on the widest possible range of astrophysical topics, of course, for objects that are X-ray emitters. Now, why is an X-ray observatory key for certain kind of studies? Because cosmological simulations tell us that the majority of baryons in the universe, if plotted on a phase diagram representing temperature and density, occupy a space where you expect these baryons to be copious X-ray emitters. So it's only natural to imagine that a powerful X-ray observatory is able to provide key clues on the nature of baryons, hot baryons in the universe. Now, let me start with the first big science question. So galaxy cluster as a probe, a large scale structure. This video is a nice representation of our universe. This is a box with a size of the order of 10 megaparsec. On the left side, you see how dark matter evolves in the universe from the origin of the universe to the current, to the local universe. And you see here redshift going down. So we are approaching in this simulation closer and closer to the current time. And on the right side, you see the corresponding distribution of baryons. And you immediately see a few obvious facts. First, that baryons, they follow the large-scale structure driven by the gravitational potential of the dark matter, origin unknown. And secondly, you immediately see that at the nodes of these filaments, there is a concentration of emission. This is where galaxy clusters are located. So galaxy clusters are a privileged probe of a large-scale structure of the universe. And if we are able to probe the evolution of the properties of the baryons in galaxy cluster from the epoch of structure formation to nowadays, we have a unique clue on the evolution of this historical, the evolution of the universe from zeta 2 to 3 to the current universe. You see also lots of explosions here, and the explosions are the effect of supermassive accreting black holes injecting energy in the intergalactic intercluster medium through either winds or powerful relativistic jets. And in fact, we know as a fact, not coming from X-ray astronomy only, that there is a strict correlation between the cosmological evolution of accreting black holes and the cosmological evolution of the host galaxies. This is shown in these two plots that represent on the left side the evolution of the star formation history in our universe as a function of redshift or look-back time from Big Bang to nowadays. And in the other colors, a proxy of the black hole accretion history. So essentially the density of accreting black holes. And you immediately see the fact that these two curves follow the same trend, which is suggestive that there is a relationship between the two things. But the relation is not a direct dynamical effect of the black hole on the galaxy, because the gravitational sphere of influence of the black hole is 1/10⁹ smaller than the size of a typical galaxy. So something happens that allows the galaxy to know how big the mass, the black hole at the center is. And this is shown also by this plot, which is one of the many incarnations of relationship between the properties related to the size of a host galaxy, the star velocity dispersion in this case, and the mass of the black hole. And the two quantities are very strictly correlated, and we don't know why. Now, Athena was supposed to be revolutionary in this field because it had a combination of three key performances. The first one is effective area. Effective area is the X-ray jargon for collecting power, the capability of detecting photons from X-ray sources. This is based on the fact that ESA has been developing in the last 20 years a new technology for X-ray optics, which is the silicon pore optics. It's developed by a company in the Netherlands, COSINE. And this technology has a few key properties. It's modular, it has high throughputs, but at the same time is low mass. You know, this kind of blocks has this side and weighs nothing. You know, you can play them volleyball if you want, you know, if you don't mind getting hit by a corner in the head. But this structure has a large area, and the area of Athena was designed to be almost 2 orders of magnitude larger than any planned and existing X-ray mission at 1 keV, and a factor of 10 at 7 keV. So we are talking of order of magnitude improvements in collecting power. The second performance is the spectroscopic capability of the mission. So the payload of Athena was, and is still for NewAthena, composed of 2 instruments. One of them is an X-ray integral field unit. It's essentially instruments capable of creating spectra on small pixels of 5 arc-second size, like any X-IFU in any other wavelength. And these are 2 plots that show the figure of merit on how well you can detect the weak lines in a spectrum, or how well you can determine the velocity of strong lines. And you know, I'm comparing now Athena, which is obviously the red curve, otherwise I would not show these plots, against an existing X-ray gratings, an existing other micro-calormeter on a Japanese mission, which is much smaller, that has much smaller optics, and with a CCD detector. CCD detector are very powerful detector in today's X-ray astronomy, but they have very poor energy resolution. And of course, I show these plots in a linear scale, so they are even more impressive, just to show you that you cannot even see the other curves. So big is the spectroscopic improvement of this mission. And the third key pillar is a survey instrument. It's the WFI, it's the wide field imager, is a depth active sensor instrument with a large field of view of 40 arc minutes times 40 arc minutes that deliver, coupled with the optics, unprecedented survey capability. And this is another of these type of figure of metric plots that you like showing, where of course the huge curve is Athena compared with what current missions like XMM Newton and Chandra can deliver. And these plots represents the number of sources that you can detect in the same field of view as a function of flux. And you see that a single shot with WFI on Athena allows you to get 1 order of magnitude more sources than any existing mission, and of course, with spectra, or even if at moderate resolution. And this is particularly important when we look at transient sources that are very common in X-rays, because we can accumulate as a function of the start time from a transient event 1 order of magnitude more counts than any existing or planned mission. Now, by using the WFI instrument in a clever way, optimizing the survey strategy, we will be able to detect a few 100,000 X-ray sources down to a confusion limit that at the time of Athena was 2 times 10 to the minus 17, comparable to that of instruments of missions with a much better performing optics in terms of angular resolution, like Chandra. Now, confusion limit is one of the parameters in the mission, I can anticipate you, that is most affected in the transition bar from Athena to NewAthena. Now, with this kind of performances, we wanted to address a few fundamental questions of modern astrophysics. First of all, well, not in any order of priority, but just question 1, or question A, if you like. How do galaxy clusters form and evolve? And in order to do that, Athena was designed to characterize the thermodynamical properties of an intracluster medium in galaxy groups and galaxy cluster up to a relatively small mass of 10 to the 13 times the mass of the sun, which is essentially the mass of small groups in our universe, and down to a redshift of the order of 1.52, which is, as I said, the key critical redshift, because that's the redshift where galaxies, larger scale structure forms, and therefore where we can actually see the origin of the baryons in galaxy cluster and galaxy group. And this means essentially doing two things. One is study the evolution of physical scaling relation that we know exist in the local universe between, for instance, luminosity and temperature in the intercluster medium. And the second is studying the entropy profile of this system. And both these things depends on how actually this system grow. Whether the growth happens through gas, which is simply accreting, falling on the gravitational potential driven by the potential of the dark matter, or there is an impact due to feedback, due to AGN or supernova. So by studying these two relationships, by studying these two quantities, we can actually have a glimpse on which of the two processes is important at each stage of the evolution of the clock. Another question is, what is the driver of the coevolution between black holes and galaxies? I told you, we see that black holes, accreting black holes in the universe and galaxy, probably co-evolve over the cosmological history of the universe, but we don't understand why. And one possible explanation is due to the presence of strong AGN outflows, winds, that actually are generated very close to the supermassive black holes, a few hundreds gravitational radii, as you say, so very close to the event horizon of the black hole. And they are able to inject momentum or energy to the interstellar medium. And since these outflows are generated very close to the black hole, the gas is extremely ionized. And the only way to determine their properties is through X-ray spectroscopy. So looking at the absorption lines that this hot gas produce when in the radiation that is emitted close to the black hole and reaches us. And this is the kind of spectroscopy that we expect on a typical object in the local universe from the X-IFU. And you see actually you don't need to be an expert in spectroscopy to imagine that these absorption lines have the potential of describing fully velocity, temperature, density, so the dynamics, the thermodynamics, and the physical condition of the absorbing gas, and therefore eventually allowing robust measurements of the outflow momentum and kinetic energy, which is impossible with current measurement nowadays at CCD resolution, which is essentially providing a key element for us to be able to answer the question, who is actually creating AGN feedback? Does actually AGN feedback is responsible for the coevolution of black holes and galaxies?
What is the kind of magnitude of the velocities you could actually see?
Yeah, here you see, these are, the most interesting of these outflows have subrelativistic velocity of the order of a fraction of the speed of light. And these are simulations with features of 0.2 to 0.25 times the speed of light, which is essentially the kind of velocity that we expect from hints that we get from very poor wiggles in CCD spectra, and are also expected on theoretical basis. So we don't know actually if we are going to measure this, but with Athena we will. And actually the important point is not measuring them in the local universe. This will be possible already with CRISM in a few months, but we will be able to make such measurements at redshift 1, 2, so where the peak of the AGN activity occurs. As a bonus, since the X-IFU instrument is a micro-calorimeter, so it's a non-dispersive spectrometer, we can make spatially resolved spectroscopy. So we will be able also to perform in a nearby cluster spatially resolved spectroscopy of the features that are probably due to the interaction between relativistic jet and intracluster medium. So another channel through which AGN can actually exert feedback, in this case, not on the interstellar medium, but on the intergalactic and on intracluster medium. A third question is, where are the missing baryons? We know that if we count the baryonic matter in the local universe, 40% is still missing. And theoretical simulations postulate that this gas, missing gas, is in the form of hot plasma that permeates the cosmic web, for instance, along the filaments of the cosmic web, of a large scale structure. But this hot gas has never been detected. There are claims of detection with RGS on board XMM with 20 days of observation that are subject of endless controversy in the community of whether these weak features are really due to a whim, due to atomic physics, due to matter in the local galaxy, in our galaxy. You know, there are no real measurements in this moment. But if we have Athena, Athena can detect hundreds of sightlines where spectra of this quality will be possible. And finally, how do spread around the elements produced by stars? Now, the intracluster medium is essentially an isolated system. So it keeps trace of the history of metal formation over cosmological time. So if we are able to measure the metallicity of intracluster medium, we are able actually to trace the different contribution of stars and different type of supernova explosion, and even put constraints on the nature of the supernova explosion that were responsible for the metals that we see. Now, this will be, of course, easily possible with spectra of this quality. This is the spectrum expected with X-IFU of the Perseus cluster, which is a cluster in the local universe. But, you know, that's an easy pick. You know, spectra of this quality have been measured. In fact, the only scientific observation of the X-ray Itomi observatory that failed 6 weeks after launch was actually a spectrum of the core of the Perseus cluster, which is not as nice as this one, but sufficient to make good measurements of the metallicity in a local universe. But what will be important for X-IFU will be able to make, once again, this kind of measurements up to redshift 2. And we will be able to get metallicity with an accuracy of the order of 10–20% for most of the metals in an X-ray spectrum up to this redshift, which is, of course, impossible with any other existing or planned mission. And here, once again, there is a bonus because you don't get only metallicities from a spectrum like this. You can also put constraints on the physics of the plasma. So on the velocities, on the density. And in particular, this is important to be able to estimate accurately the total mass of a cluster, which is a key ingredient in order to do cosmology with the distribution function of the cluster masses. Now, this is just a few examples of the kind of scientific questions we want to answer with Athena. But as I said, Athena was supposed and designed to be an observatory, covering all the possible scientific topics on X-ray emitting celestial sources. And now this slide is purposely written with small characters. So my goal is not that you read it, but my goal is simply to impress you, because this is the list of a science cases that had been designed for NewAthena. And the list is 36 cases. So 36 cases going through cosmology using clusters and AGN to AGN at high redshift, 2 planets in the solar system going through galaxy cluster, supernova remnants, supernova explosions, stars, compact objects, and eventually what the observational program of an observatory at ESA is will be driven and determined by the community at the time Athena flies. That's why it's not surprising that there was lots of effort spent in seeing what Athena can do in stars, on stars, planets, and exoplanets. And now we enter in the field on which, you know, my knowledge, direct knowledge, is the least. So once again, I have to take thanks all the colleagues of the Athena community, the star community and the exoplanet community for all the work that they have done on Athena, and more recently, they are doing to support me on NewAthena in these fields. But there is something there's something in comment I would like to make, but I will make it later, specifically on exoplanet. Now, stars are also X-ray emitters, and different phase of the star evolution from, you know, falling from the protostar phase to a main sequence star they emit X-rays to a different degree and due to different mechanisms. Now, interestingly enough, I have worked with stars in X-rays in my life, because in my previous incarnation, before working for Athena, I was a calibration scientist on XMM. And we use stars for calibration because they are strong emitters with long emission lines. They allow us to do calibration of heavy quantities. And I remember having given talks on calibration topics saying, and now CU, the spectrum of Capella, which is, as you all know, is due to the coronal emission of the star. And of course, this is wrong, because depending on which phase of a stellar evolution we're looking at, we may be looking at magnetic reconnection events on a star, like we see in the solar corona, but we may be looking at completely different things. For instance, if we look at the emission of early young stellar objects, these young stellar objects, I will show you in a minute, they not only is not obvious whether the X-ray emission is coming from coronal processes or not, but in addition to that, their interest is not limited to the fact of what they tell us about the stars. It's important also for what they tell us about the physical and chemical evolution of protoplanetary disk. So stars are not only much more varied and differentiated in X-rays than I used to say when I was a calibration scientist, but their interest is not only directly for the stellar physics, but also for the study of planetary and exoplanetary physics. Now, let me go through a couple of the science cases that have been studied by the scientific community of Athena so far. One of them is the nature of X-ray emission in young stellar objects. As said, it's not obvious and it's not granted that the mechanism responsible for X-ray in young stellar objects are the same that we observe on the sun. And in fact, there are some initial evidences that the X-ray emission in this object could actually be due to accretion shocks rather than standard coronal processes. And now, the way to discriminate it, to understand whether this is the case or not, is looking at the density of the X-ray emission and at its time evolution. If we measure the spectrum of a thermal plasma, of an optically thin, collisionally ionized plasma, studying of specific transitions that are the helium-like triplets provide us with very strong constraints on the density of the matter. So now we have nowadays with RGS some measurements of the density of young stellar objects for nearby strong X-ray emitters. But what we would like to do, and actually these also provide some initial indication that actually accretion shocks could be a dominant component of the X-ray emission in this nearby object, in these few nearby objects. But what we would like really to do is to make a time-resolved spectroscopy of the emission of the star in order for us to be able to trace through density evolution the nature of these shocks. And this will be easily possible with Athena on nearby objects, because just 1 kilosecond of X-IFU could allow to get a spectra of this quality, which corresponds to a density of the order of 10 to the 12 square centimeters, volume centimeters. And you can imagine that if I get a snapshot every hour of spectra of this kind, and the ratio between lines changes, it's very easy for me to determine high light curves of the density evolution in these systems. But also for those systems that are too far away for Athena to be able to get a time-resolved spectroscopy, just a measurement of density will be able to make give a clear indication of the nature of the X-ray emission. As shown in this simulation where I compare, well, somebody compares the spectrum expected in the case of a coronal plasma with crosses with the spectrum expected for an accretion shock with a much larger density. Another thing that will be easy to do with Athena will be study stellar winds. Now, massive stars, we know, exhibit stellar winds with velocity larger than 1,000 kilometers per second. And we know that they are both small and large scale structures, probably due to dynamical instabilities in these winds. I studied a little bit the study of stellar winds in close to compact accretion object, and I know what simulations show in terms of extremely clumpy and patchy stellar winds in this system. Now, these kind of large wind structure are important not only because we want to understand the dynamics of these winds, but because if we don't know the nature of the clumps, we don't know the covering factor, and we don't know their numbers, their density, we can't actually understand what the mass loss rates are. So there are enormous uncertainties on determination of the mass loss rates, which of course is important if we want to understand the role the stellar wind have on the evolution of the stellar mass and rotation. Now, of course, you can try doing this kind of measurements nowadays, because if you have a wind and this wind have clumps and this wind is emitting X-rays, the structure of the clumps affects the shape of the lines. So by looking at the shape of a line in a time-integrated spectrum, you get some glimpse of what the distribution of these clumps could be by comparing the observed spectra with magnetohydrodynamic simulation. But what you would like to do is to make a direct measurements of these clumps. And this requires a time resolution spectroscopy, which will be possible on Athena. You expect, for instance, that if these clumps are present, and these are due to winds, these winds are related to the rotation of the star, and therefore you can actually, by making just a 1 hour X-IFU exposure of a standard star like Zeta Papis on the, for instance, 10 neon line, you will see how actually this line evolves with the rotation of the star, and therefore getting, for the first time, physical constraints on this question. So X-IFU opens a way on the one side of enlarging the star samples on which these measurements are possible, but also, and more fundamentally, on time-resolved spectroscopy. And this is not only for winds in isolated system, but also for even brighter winds, colliding winds in binary system. And we know that 50% of all stars are in binary system. And we know that the shocks, the shocks that are generated when winds coming from each of the components of the wind collides provides a very interesting laboratory of shock physics that can be probed with the accurate spectrometer like Athena by studying the light orbital changes along the phase of the orbits of the binary, especially the binaries are in an eccentric orbit. Going back to the plasma flares, another thing that we would like to understand better is the dynamics of the plasma during stellar flares. And this requires making revelocity measurements of the plasma on time scales that are of the order of the initial evolution of the flares. Now, these flares is a collection of flares in AB-DOR, I think. It's a collection of light curves from the RGS experiment instruments on board Dixon and Newton. And the scale on the x-axis is difficult to read, but essentially it's order of half a day to a day. And these flares are very open very fast. They have a rise time of the order of 1,000 seconds at the most. So if you want to know what is the evolution of the density during this flare and what is the evolution of the velocity of the plasma during this flare, you need to create a time-resolved spectroscopy on this time scale. Now, try to do it with RGS, and that's what you get, pure noise. That's why it has been attempted, but never really done with XMM. But that's what we get with X-IFU on an average flare. And by the way, this is the spectrum in the soft X-ray band, where the collecting area of all X-ray telescope is much better. This is a spectrum around the iron helium-like ionized line at 7 keV, where the collecting area of all X-ray telescope is much lower. And despite of that, measurements of the velocity of the order of a few hundred kilometers per second are really a piece of cake. And these will enable measurements not only of velocity, but also density and abundance. And this leads me naturally to the subject of exoplanets. And let me make a pledge before I start showing some simulation or possible results on exoplanets. There has been lots of work in the stellar community in terms of simulations with Athena. And what I've shown are all simulations done by people who know much more than I do in the subject. But historically speaking, the subject of exoplanet with Athena has not achieved the same level of high profile. So there essentially has been no real Athena simulations done on exoplanets. And the first kind of Athena simulation has been done recently by Rachel Austin in this context that I'm going to show in a second. So there is really lots of rooms if you believe that a mission like Athena could give a contribution to exoplanet science to do novel work that has not been done so far. Unless it has been done and I'm not aware of it, in which case it's just a source of my ignorance. But I think there is really room to contribute originally to this field of research in the new Athena community now. So let me go back to the flow of the presentation now, because one possible interesting subject is the exploration of stellar flares that are actually not due to magnetic reconnection phenomena in the star, but actually due to are triggered by interaction with the planets. And once again, this requires doing time-resolved spectroscopy on very short timescales, hundreds of seconds, which is once again possible only with Athena, but very easy with Athena at the level of velocity that we expect. And these are simulations done by Rachel Austin on a typical star, on a star hosting, possible hosting, planet hosting star. And of course, in itself, if you look at a flare, you don't know by itself whether this is due to magnetic reconnection or a planet interaction, but by comparing a large number of events in systems that host or do not host the planets, and of course, by comparing the observed properties with the adequate simulation, you can actually get a glimpse of which subset of these flares could actually be a signature of iteration with the planet. Results obtained so far in this moment are indicative but not conclusive. There will be a few studies trying to see whether there is a correlation between flare properties and planetary phases, for instance. We are still at the infancy. This is an example of a source which has been studied for 8 years by X-ray and Newton, and still you get only tentative results. So, of course, it may be possible that maybe XMM gets some robust results by the end of the 2030s on a few objects. But if you want to do sample systematic studies, a much larger X-ray observatory is the only way. Another point on which X-ray spectroscopy can be very useful for exoplanets is the study of exoplanet photoevaporation. Now, even if you know what happens in X-rays, in order for you to be able to assess fairly the impact of radiation coming from the star on the atmosphere of an exoplanet, X-rays are not sufficient. You need actually the whole spectral energy distribution from extreme ultraviolet to X-rays. So in a sense, you have to extrapolate the information that you get in X-rays to lower frequency or to longer wavelengths, if you like. Now, if you have a full X-ray spectroscopy on one side and full UV spectroscopy on the other side, extrapolating to the extreme ultraviolet is relatively easy. I don't want to say it's easy, of course. There are surely plenty of physical uncertainties, degeneracy, complication, but it's conceptually possible. But if you have just the X-ray spectroscopic measurements in X-rays, or you don't have X-ray measurements, this is a mission impossible, not possible like the comics over there. So in order to address this problem, you can actually use a certain kind of approximation. You can still use CCD spectroscopy measurements and try your luck. Of course, you can just use X-rays if you don't have UV, or there are lots of scaling laws that have been calibrated, among them by Manuel and this group recently, connecting LX and AUV. But the power of X-ray spectroscopy in this field is obvious. And once again, it's a low-hanging fruit for X-IFU, because these are relatively simple measurements for a spectrometer, which has been designed to do spectroscopy of galaxy cluster at redshift 2. Another field where we expect X-IFU to be able to give a contribution is the study of coronal mass ejection. Now, I don't have to pledge to this audience that understanding more for coronal mass ejection is important, not only for us to understand better the physics of stars, but to understand the star mass losses and momentum losses. But also it's very important to understand the potential hazard that CMEs can represent to planet habitability. And but we don't have an easy way to determine if there is a CME associated with flare loss, beside our capabilities, our extrapolation of what we see in the star. But we know that in the star, something very peculiar happens most of the time that the flare happens. And once again, here I'm pledging to the course because I'm extracting results from a paper that was published from the group here. So I'm not saying anything new probably to the audience, but you know, when we see a flare on the star, we see also a dimming region in the light curve of that is extreme ultraviolet and soft X-rays, which is essentially a signature of the fact that when we have a flare, most likely matter from the CME has been ejected, and so the footprint of the coronal loops have been deplenished of matter. And as said, since there seems to be a stronger correlation between CME and dimming, getting a proof of CME mass loss dimming in a star can be a very good handle to get a glimpse of the existence of a CME. And not only that, if we can get a measurement of a reduction of the emission measure after a potential coronal mass ejection event, we can also make a direct measurement of the mass outflow and therefore get a glimpse on whether the CME is representing an hazard for the habitability of the planet if the star where the flare happens, of course, hosts exoplanets. Now, in the sun, whenever dimming happens, it happens actually in lines. So this is shown in this spectrum where the dimming effect, so the effect of the dimming is shown by the blue curve. And you see actually lots of absorption lines. So you can actually measure this dimming in lines. So if the same happens for an hotter star, we can actually see this dimming effect in emission lines in X-IFU, which once again highlights the potential power for the spectroscopy of the spectrometer of this kind. Now, of course, we would like to get the direct X-ray spectroscopy of a CME, maybe measuring outflow velocity in spectral lines. This is also something that with X-IFU will be possible, as simulation I've shown before also demonstrate. And this is another field where the improvement with respect to existing mission will be huge. Now, this is a result that has been obtained on the potential outflows associated to flares in a star with a Chandra high energy transmission grating. And, concentrate your attention to this curve, which represents the evolution of the velocity as measured from X-ray spectroscopy as a function of time during and after a flare. So you see actually there are some hints, evidence, tentative evidence of changes of velocities that allows you to measure the dynamics of a potential CME. But the error bars are huge. And this is once again something of which X-IFU will allow you to get error bars 1 order of magnitude lower. There is not only field for room for spectrometers, but there is also room for new survey science. For instance, looking at the coronal properties of large sample of stars in the WFI survey. Now, this has been attempted with existing data, going back to Rosat in the 90s, and then with XMM and Chandra, and always with samples that are not bigger, not larger than 50 objects. And these results, you have 4 studies, 2 says one way and 2 say the other. 2 says that there is actually evidence for increased coronal activities in correspondence to planets, larger planets, close in, and other studies say, no, generally this doesn't happen. So once again, you need a real statistic. You don't need just a handful of objects. Now, the Rosatowski survey contained 40,000 FM star with a flux larger than their flux limit. The stellar content of the Chandra cosmos, which is 1 square degree, is already 60 stars in the same stellar range. So if you extrapolate to a large field survey covering several thousands of square degrees, for instance, that is what's possible for WFI, you get easily tens, hundreds of thousands of stars on which this kind of studies are potentially possible. And the comparison between the Chandra cosmos field and NewAthena confusion limit is not by chance, because essentially the flux limit of these 2 surveys is comparable with the new mission. Last topic, but not least, is the potential of detecting charge exchange. So charge exchange, which is the signature of interaction of high energy radiation with neutral environments, has been already detected with XM and Newton on planets. Been detected on Jupiter. In this case, with the interesting implication of studying the plasma dynamics on Jupiter, velocities of the order of 1,000 kilometers per second were detected. Origin is still unknown, could be origin of the solar wind, could be origin of the eye of volcanoes, and only Athena will be able to tell with the spectra of these qualities. And also we have detected with XM and Newton solar wind the charge exchange in Mars. Now, of course, solar system measurement with Athena will make advantage of the non-dispersive nature of X-IFU, which is not relevant for exoplanets, but still a few stellar targets have been identified, where in principle it would be possible to measure solar wind charge exchange, a system that actually hosts planets. Now, I just put here for your reference, this presentation is available, of course, for you later for further consideration. Another list of topics that I didn't have time to cover, and in fact, I'm 4.5 minutes away from the end. And in general, if you want to know more, please refer to the Athena white papers that discuss these topics and discuss each of these topics in much more detail. Now, I have the two final slides on where we stand, because I have told continuously on Athena, but you know, the reality is that Athena does not exist any longer. Athena has been suspended by ESA in June 2022. And the reason is that at that point, and this has been confirmed later by independent studies, Athena was discovered to be too expensive for ESA. And not to mention the cost to the member states, of which ESA, of course, cannot syndicate. But for ESA, it was simply too expensive. So the mission was terminated. But the SPC, who is essentially the body who is running and ruling the content of the science program of the agency, mandated ESA to study a new mission concept that, with some lack of originality, has been tentatively christened NewAthena. Now, NewAthena has to fulfill the two conditions. First of all, it has to be cheaper by a 30% with respect to the original cost of the mission. But at the same time, it has to retain science capabilities, making of Athena, NewAthena, a flagship mission. What this means in practice, we don't know. But of course, that's one of the questions that we need to answer. Now, this happened in June last year. In March this year, ESA announced that after lots of hard work, such a new technical concept has been identified. Now, this concept exists. It seems to work. It may, we may start a new industrial study, phase A, as we call in ESA jargon. But we still need what is called the programmatic consolidation, which is the ESA executive jargon to say all partners have to confirm that they are willing to pay the money that we need from them. And all partners means NASA, means JAXA, and means the member states. And, you know, they are making their calculations, and they are actually preparing a letter saying, yes, we can give you what we promised to deliver. No, we can't. We expect that everybody is going to say yes, but before this happens, and this will happen only at the meeting of the SPC in November this year, the mission cannot restart. In parallel, ESA appointed a science redefinition team to advise on the new Athena science, which has different various tasks, among them defining the new Athena science objective and requirements, confirm that new Athena is a flagship mission, whatever this means. And we have already completed in this framework a full review of the Athena science cases, and the validation of the new mission profile on a small number of science objectives is ongoing while we speak, and will continue until October of this year. And at that point, we have to report eventually to the advisory structure. Now, this is new Athena. New Athena is essentially the same as Athena, but with performance that are compatible with the new cost environment, which means an effective area at 1 kV of 70–90% that of Athena, an angular resolution of the optics that will be somewhere between 5 and 9 arc minutes on axis half energy width, and 5 was a requirement for Athena. An energy resolution of the X-IFU between 3 and 4 electron volts, and it was 2.5 with Athena. A field of view of the X-IFU of 4 arc minutes instead of 5. A field of view of the WFI between the current one and 30 times 30, but most likely the large one will be retained. A slightly lower background level for the WFI. A lower background knowledge related to the lack of a specific hardware, a particle monitor that was designed to monitor the background. A smaller field of regard. The field of regard is the fraction of the sky that is visible at any single moment in time by spacecraft, and a delayed response to target of opportunity. Now, the current assessment of the science definition team that I'm co-chairing is that most, but not all, of the Athena science objectives remain achievable with NewAthena. And as said, we are making a quantitative assessment of this statement to be ready by October this year, to support any decisions that the SPC will make, hopefully in favor of NewAthena to start. So that's my summary. So the take-home message, the key one is we went through a serious financial crisis, but Athena is dead, but the Athena science is not dead. The Athena science is still under consideration by ESA, and we could resume phase A of a new mission if everything goes fine at the beginning of next year. Now, I try to learn, and I desperately try to convey that there is lots of extraordinary science that Athena and NewAthena will be able to do, both on stellar science and exoplanets. And we expect that NewAthena will be able to retain most of the science objective of the mission. And as I said, the SRDT is a group of 17 scientists. They don't cover all the science of Athena. This would be impossible. So if after this talk, or independently, you believe that NewAthena could be your mission, we are more than welcome receive any contributions to improve the science case of the mission, in particular on stellar planets and exoplanets and solar system, but of course on any aspect of the Athena science. And if you have any inputs, this is the right moment to provide these inputs because it can really help us in supporting vis-a-vis the politicians the case of a larger scale observatory in the 2030s. So with that, I thank you for your attention and I welcome any questions you may have.
All right. Questions from others than me? I have one. Do we have students who have questions? Not really. Let me start with Rumi.
Thank you very much. This is very impressive. I'm not exoplanet scientist as well as not Athena scientist, so my question is a bit off maybe. But I thought interesting. I'm doing more plasma science from the main solar system based on in situ. But you talk about your language, like your AGN, this explosion, and you see these shocks and so, and you talk about the hot plasma, and I think I can see that there are quite commonality that we are doing in situ in the science. And just my curiosity is how the resolution can be, can you identify the shock surface, and then you can talk about the temperature or plasma
yes,
change. And
for a galaxy cluster, this is possible for the nearby objects because we see in the morphology of the X-ray emission of galaxy cluster lots of structure, ripples, cavities, and some of them are most likely associated with shocks. So with Chandra nowadays, we can do imaging and very poor resolution spectroscopy, but with Athena, we will be able to perform spatially resolved spectroscopy exactly on the spatial scale of the structure. And in fact, this is one of the main drivers of the spatially resolved capability of the mission, being capable of measuring shocks, for instance, on scales of the order of a few arc seconds. This is, of course, not limited to cluster. It will be also possible, and with probably even better spatial granularities in supernova remnants, for instance,
Jets,
where you can jets, of course, in galaxy clusters, but of course also in AGN jets. You can study once again in the local universe, not in the jets. The issue with jets is in the local universe, they tend to have weapons actually on scale which are of the order of a few arc seconds, so they are marginally consistent with the capability of Athena to resolve them. But for the objects close like M87, it will be obviously possible.
Okay, I have one more. Sorry, this your way of saying that planetary induced flare or magnetic reconnection. I was a bit surprised because usually planetary magnetic energy is much smaller, and compared to the star. So I don't know the exoplanet, whether you find in the exoplanet community that that's kind of big energetic, magnetically, I mean, strong magnetic field that you can affect really the reconnection, the flare. I'm a bit surprised because in a solar system, we cannot think of planetary. I can understand that the solar wind induce the reconnection with the planet, but you are talking the opposite way, and I found it very interesting whether you can resolve this or is it some simulative imaginary thing? Or I'm surprised the way you said. Okay.
Oh, sorry, I forgot to relay the question. I was asked to relay the question. So whether okay, the microscope. Okay, so you don't resolve them in the sense, my understanding is, bear with me if I'm saying something incorrect, but my understanding is for a given flare, you cannot tell whether this given flare was due to an intrinsic magnetic reconnection event or to event that was triggered by something else. But if you look at the sample of the flares and you find a correlation between the sample of the flares and the orbital phase of the planet, or if you can see a systematic difference in the nature, in the coronal activity of stars hosting exoplanets and not hosting exoplanets, at that point you should ask the question, do have the planets something to do with these differences? So that's, I think, the approach, or at least the spin I was giving in describing the science case.
Both you can see it at the same time without resolving it. So still sun-induced reconnection of the planet.
You don't see them resolve, of course. Yes, you don't see them resolve, of course. That's clear.
It is very controversial.
Also of Jupiter, so not
No, I don't have to compare, but even I'm surprised with what Jupiter actually is in, or what Jupiter star is induced by what Jupiter.
I think you want to look at the spectrum. So this is a huge controversy in the field, and I think we have four examples for which that has been postulated. Yeah, I think Peter was next.
I was interested in measuring the metallicities, and I wanted to ask, it's very interesting to put star formation and planets evolution into a galactic context. So we would like to know maybe more facts about how the metallicity is actually distributed in galaxies and how that possibly also involves in time when you can look back into galaxies. So can you say maybe, could you also measure this in our own galaxies? Say not the intercluster medium, but the interstellar medium or the interspiral arm or whatever. So I don't know. Or is that not possible in our own galaxy? You always have to look at extragalactic sources?
What you look in order to measure metallicity is not the interstellar medium in a single galaxy, but the intracluster medium permeating the space among galaxies. So this kind of measurement is not possible in our galaxy because we are not in a cluster. But what surely we expect to be able to do is to measure the physical condition, including the metallicity of hot halos surrounding nearby galaxies, similar, for instance, to the Milky Way in the local universe. Components like, starboard-driven outflows or circumgalactic medium. These are structures that are predicted by cosmological simulation. So we expect them to be present around galaxies in the local universe up to 200 kiloparsec. We have started seeing evidence of this in stacking lots of images of Rosetta, for instance, so of shallow X-ray surveys. In fact, we know of the existence of this CGM since the Rosa time, from an observational point of view. But in this moment, it is impossible to measure physical properties of this gas. But we, Athena, we will be able, first of all, with the survey of the WFI, to get a much larger sample of these components. And then with specific measurement with the X-IFU, which is a small field of view instrument, we will be able to measure also velocity, metallicity, and density of these components. So I don't think, it's not obvious to me if it is possible to be done, in our galaxy, because the question is of separating the component. But it's surely true for possible for galaxy of the local universe. Of course, we measure lots of components of diffuse gas in our galaxies. They have been known as in the Rosa time, and on which Athena is not going to say anything more about that. Yeah, but matches. Yeah.
Okay. You talked about the local universe, which is redshift 0, right? But Athena is able to observe higher redshifts.
Yes.
What does it imply in terms of instruments? So I have no understanding of how much EV are shifted by the redshift. What does it imply for the instrument? Like, do you lose resolution? Of course, you use flux. So can you tell us more about it?
Well, the impact of looking at high redshift universe is twofold. On one side, inevitably sources are weaker. So that's where the collecting power comes from. And, it changes a lot between now, the current universe and Zeta 2. And even more if you want to look at, for instance, AGN at redshift 6, you are looking at objects with a flux which is 4 to 5 order of magnitude weaker than the typical AGN in the local universe. So you need much more effective. In terms of energy shifting, if you look at redshift 2, all your spectral features are shifted by a factor 3. So if you're interested in an iron line at energy 6.7, in your observed spectrum will be at energy around 2. So this means, and that's the reason why the effective area of Athena was maximized at 1 keV, that you have to have your maximum collecting power if you want to study a higher redshift universe in the soft X-ray band. And the soft X-ray band, it's not difficult because it's essential, so natural what you get from physics. But the effective area of Athena is maximized, in fact, exactly at 1 keV, exactly for this reason.
Okay, I think I would like to move all further questions to later on, because we're already after the hour. Matteo, thank you so much for this overview and for this enchantment with non-cosmological aspects. I think at least I have appreciated this hugely. And I welcome now everyone who wants to join the conversation into, what was it? Mars, Mercury? In about 25 minutes upstairs. So